Okay, so the recording has started. Great. And without much ado, welcome everyone to the Recurrent ETDS seminar. Today, to our pleasure, we have Jacob, who will be telling us about arithmetical subword complexity of automatic sequences. Over to you, Jacob.
Thank you very much. Thanks for the invitation, and thank you to everybody for coming. I'm going to be talking about arithmetical subword complexity of automatic sequences. And with that in mind, let me start saying a couple of words about complexity in general. So our general setup is going to be that we have a sequence over some finite alphabet omega. If you happen to be at the Department of Computer Science like I am right now, you might want it to be a binary sequence over 0, 1, or it can be some other alphabet of your choosing. And natural question is, well, how complex is this sequence? And this question may be natural, but it's also extremely vague. So let's look at some specific measures of complexity that we might be interested in. So the most classical notion here is the subword complexity, which basically measures the number of subwords of A of some specified length. This notion is, of course, connected with topological entropy, in that if we consider the associated shift space, then the topological entropy of this shift is going to be just the limit of the logarithm of the subword complexity normalized by, well, the length of the word. These two notions are very classical and well studied. The notion that I'll be talking about today is arithmetical subword complexity, which measures not subwords that appear as a consecutive subsequence, but subwords that appear along an arithmetic progression. And it was introduced by Augustinowicz, von der Flass, and Fried. And here, there doesn't seem to be any natural link to dynamics, although I would be very happy to be proven wrong about that. Another slightly related notion is polynomial subword complexity, where instead of looking along an arithmetic progression, we look along polynomial of some fixed degree d. And there's a lot of other related notions such as decomplexity, maximal pattern complexity, asymptotic subword complexity, and so on. People who do combinatorics on words introduce a lot of those notions, but they will largely not be very relevant to the talk at hand. So,
Jacob, so we just focus on the arithmetical subword complexity, right?
We'll mostly be interested in arithmetical subword complexity. Keep in mind subword complexity because it's a very classical notion and it's going to come up a couple of times. And occasionally there will be some results which apply to polynomial subword complexity, which I will briefly point out, but I will not focus on this too much.
I see. And so you mentioned that this might have some link to dynamics, but might not. But isn't
well,
it
I'm not aware of any link to dynamics, but I would be very happy if somebody came up with something. Just wanted to throw it out there.
Okay.
Like if some smart dynamicist can think up of some dynamical interpretation, that I think that would be quite interesting. But
so this is not just looking at the power of a map, right? If I looked at all powers of a map, that wouldn't exactly capture this because you're looking only at letters along an arithmetic progression, not the blocks that you see.
Well, it's sort of like looking at the power of the
Shift map.
of the shift, but you're looking at all the powers at the same time. So I'm not sure how you would capture that.
Okay. Okay.
Okay. So just a couple of brief words about subword complexity to kind of acquaint us with the subject. So subword complexity is always between 1 and the size of the alphabet to the power the same as the length. The periodic sequences are the simplest ones. They have bounded subword complexity. And conversely, if subword complexity of L is less than L for at least one L, then our sequence has to be eventually periodic, which is nice exercise. And the classical Sturmian words can be characterized as the words with the least possible subword complexity. So they have subword complexity exactly L plus 1. And this is an even odd if. And for automatic sequences, which I'm going to be mostly talking about today, have subword complexity that's very low, but not quite as low as Sturmian sequences. So this complexity is going to be linear, which is up to a constant, the least possible. Now, I'm guessing a lot of people will not be very familiar with automatic sequences, so let me briefly try to introduce them. And here the best way is to explain by example, and the most classical example is the Thue-Morse sequence. So the Thue-Morse sequence is the plus minus one valued sequence that whose initial terms you can see on the slide. And there are several ways to define it. So as in terms of an explicit formula, it's plus or minus one depending on the parity of the sum of binary digits. I think that's terminology coming from Conway, who called them evil and odious, in honor of the sum being even or odd. Now, it is an automatic sequence. On the next slide, I will explain exactly how automata work, but here's an automaton that computes the Thue-Morse sequence. Perhaps you can already guess how it works. It can be given by simple recurrence formula, where I define the value at 0, the value at 2n in terms of value at n, and the value at 2n plus 1 in terms of value at n. It is the fixed point of a substitution. So we have the substitution that you can see over there. And if you start with plus 1 and you keep applying the substitution, you're going to get longer and longer prefixes of the Thue-Morse sequence. And it also happens to be a strongly multiplicative sequence, meaning that if you want to compute the Thue-Morse sequence at some integer, then you can break up this integer into the digits of this integer into two blocks, compute the value of each block, and multiply those values together. Okay, so these definitions are all sort of special cases of ways in which automatic sequences can be defined in general. Now let me try to make this a little bit more precise. So I'm going to need some notation. I'm going to use sigma k to denote the digits base k. Sigma k star are going to be words over sigma k, so strings of digits. For an integer n by n in round brackets, I'm going to denote the base k expansion and conversely for a string of digits w, by w in square brackets, I'm going to denote the integer encoded by w. Now, an automaton is going to consist of a bunch of states. So these are depicted by circles in the picture, and one of them is distinguished as the initial state. We have a transition function which tells us, given a state and a digit, what's the next state that we should go to. This is depicted by arrows. And we have an output function, which is depicted by labels on each of the nodes, which basically tells us if we end up in a specified node, what value should we output. So in order to use this automaton to compute a sequence, we first of all extend the transition function by saying that, well, if I read a string of digits uv, then first follow the path encoded by u, and then follow the path encoded by v. And the nth term of the sequence is going to be obtained by starting at the initial state as not, then following the path encoded by the digits of the integer n, and then at the state where we end up, we read out the output function. So as an example, this automaton that I used for illustration computes the second most famous automatic sequence, which is the Rudin-Shapiro sequence, which is plus or minus one, depending on how many times you can find a pair of consecutive ones in the expansion of n. Now, this might be a bit of a convoluted definition, but for the purposes of this talk, it's mostly going to suffice to remember that an automatic sequence is computable by some finite device.
So just to be clear, I've always seen several definitions of automatic sequences, but like I'm sort of most comfortable with the substitutions. So here is this
Yeah,
is it?
that's actually the next slide.
Oh no, but like I do want to understand how the other sequence works. So I can think of a graph where the symbols of my sequence will be labels of the vertices of the graph. And then the graph will have zeros and ones. So there are two, right. So each vertex has exactly one outgoing zero, one outgoing one.
Yes.
And so that sort of determines how to read a sequence given this graph.
Exactly.
Yeah.
So you start at the initial state, and then you look at the consecutive digits of your number, and you have one edge. And if you read a one, you go to the state with the arrow one, and if you read a zero, you go to the state with arrow zero.
But your automatic sequence is an infinite sequence, right?
Yes. So I'm explaining how to compute the nth term of the sequence. So I have so if you want to compute, I don't know, a of 43, you write down 43 in binary. It's some string of digits. It corresponds to some path in the graph. And this path is going to either end in a state with a +1 or a state with a -1. And then depending on which of the two it is, the value of the sequence is + or -1.
I see. Oh, wow. And that's equivalent to, okay. All right.
Yeah, that's
substitutions.
That is equivalent to substitutions because they kind of...
I see.
Yeah. Like if you're reading the digits from the most significant one, then you can sort of go between the two descriptions quite trivially. Okay, so like Nishant hinted, the people coming from dynamics might be more familiar with the definition through substitutions. So let me very briefly introduce that as well. So by substitution on some alphabet lambda, I mean a map that assigns to each symbol in lambda some strings of symbols. And to make our lives a little bit easier, I'm going to assume that at least this substitution doesn't erase any symbol, so each symbol maps to a non-empty word. Now, if I have a substitution, it induces a map on words on infinite words over lambda, just by applying the substitution to every single letter consecutively. Now, a substitution is k-uniform if the length of if each letter maps to a word of length exactly k, so it it increases the length of words by a factor of k. By a letter-to-letter coding, I mean just application of any map symbol by symbol. And with this language, I can say that a sequence is k-automatic or automatic in base k, even only if it is a letter-to-letter coding of a fixed point of a k-uniform substitution. You presumably know that there's a lot of theory about dynamics of substitutive sequences, of the shifts generated by k-substitutive sequences, but I'm not going to talk much about that. Okay, so coming back to the subject of subword complexity, subword complexity of automatic sequences is very well understood. So in a lot of cases, you can just compute this complexity very explicitly. For instance, here's a formula for the complexity of Thue-Morse. It's just some formula. There's a couple of cases, no deep philosophy there. As a general rule, automatic sequences have linear subword complexity, and here a proof is actually very simple, so I might as well very quickly go through it. So if you think about if you cut up your sequence into blocks of length k to some power alpha, then each of those blocks is determined just by the state of the automaton that you reach after reading, well, the digits except for the last alpha positions. So if I have any word of length k2 alpha, then this word appears somewhere in the concatenation of two such consecutive standard blocks. So in particular, the word of length k2 alpha is determined by the state corresponding to the first block, the state corresponding to the second block, and the position where it appears. So we get the subword complexity at k2 alpha is at most the number of states times the number of states times k2 alpha. So it is linear, and if your length happens not to be a power of alpha, just sandwich it between two powers of alpha, and you get your result. Okay, so that's not as much as I can tell you about subword complexity of mathematic sequences, but we were going to talk about arithmetical subword.
Sorry, I didn't follow this so well. So sorry for slowing you down.
No worries.
Yeah. So you're looking at okay. We want to count the number of words of this automatic sequence, and each letter is generated by reading out the number in your graph. That's how I should think about it.
Yeah.
And now go ahead.
So if I have a block of length k2 alpha that starts at k2 alpha times some integer n, then whenever I compute at a term of the sequence that belongs to this block, I'm always going to first read the digits of n, and then I'm going to read some consecutive digits.
Right.
So if I know which state I reach after reading the digits of n, that tells me each entry in this block. So this entire block is determined just by one state in the automaton.
Right.
Or if you prefer thinking about it in terms of substitutions, this basically says that if I disubstituted, then all this block just comes from applying the substitution to power alpha to one symbol.
Right.
And then I say that if I have an arbitrary word of length the same as this block, then then I can cover it by two of those standard blocks that start at the power of k.
Right. Okay. Thanks.
Sure. Okay. So as I mentioned, we were going to talk about arithmetical subword complexity. So we're interested in complexity along some specific type of progression. Now, a general theory a general heuristic in the theory of automatic sequences is that if you have some subsequence, say m of n, that somehow doesn't know about base k digits, or to be more specific, let's say we're specifically talking about Thue-Morse, so let's say that our sequence doesn't know about binary digits, then Thue-Morse sequence should look mostly random along the subsequence. So what do I mean by random? Well, I mean that I should have plus or minus ones equally often, which numerically just corresponds to vanishing of the cancellation in sums in averages. I expect that this sequence would actually be normal, meaning that if I look at subwords, all of them appear with correct frequencies, which arithmetically corresponds to cancellation of multiple averages like the ones up there. And in particular, I would expect to have maximal subword complexity. And this is actually a very active area of study. It tends to be quite difficult, surprisingly. So for instance, if you want to understand the sequence, the Thue-Morse sequence along the squares, then this was done by Modwi and Riva, who showed that this sequence is normal. Very recent, relatively recently, it was like maybe a year ago, Lukas Spiegelhofer was able to show that Thue-Morse at cubes is +1/2 of the time. I think normality is still not known, and any higher powers are very definitely not known at all. You can do fractional powers, So look, Müllner and Spiegelhofer showed normality for n to power between 1 and 3 halves. There's results about primes, but that's about as much as is known. But well, in our case, we are talking about an arithmetical progression. And as a matter of fact, this theory doesn't quite apply there, because if you look at the Thue-Morse along an arithmetic progression, then it's again going to be an automatic sequence, and hence it's going to look very non-random. I'm hoping to still recover some sort of randomness by looking at Thue-Morse not along a fixed arithmetic progression, but along some sort of a randomly chosen arithmetic progression. And
So just to be clear, when you say that something doesn't know about binary expansions, is there, so you're looking, so you're choosing your MNs in a very particular way, right? Squares, cubes, something non-linear, and now arithmetic progressions, I guess.
I'm just thinking about something, some sort of a natural sequence. So if I pick Mn to be, say, the nth number whose sum of binary digits is even, then obviously Thue-Morse is not going to look random along that.
Right.
But like if it's something natural that I define without using the word binary expansion, then probably it's going to work.
I see. So, like, is there a rigorous way of saying this?
Oh no, not at all. This is a purely intuitive notion.
Okay.
It's just a heuristic. Okay, so the thing that we're going to use in order to talk about random arithmetic progressions is the higher order Fourier analysis, which I'm going to now try to very briefly introduce. So the central object that we're going to be interested in is the Gauss norm of a sequence. So the most succinct way of defining it is as follows. Let's say that we have some function f on the initial interval of integers of length n. Let's say that our sequence is complex valued. And now I define the UD norm by evaluating by looking at, let's call them parallelepipeds in n. So these are going to be 2 to the points, which are basically obtained by picking a d tuple of integers n1 up to nd, and considering, and also picking some starting point and not, and then considering, so think of those ni's as edges, and we add any subset of those to f, to n naught. Now, those are going to be the vertices of our parallelepiped. And now I'm going to evaluate f at all of those vertices. Every second one of them I'm going to conjugate so that the resulting function ends up being a positive definite. Then I'm going to average over all parallelepipeds. And then I'm going to take the 2d root. Now, this looks quite, perhaps, quite abstract at the, well, maybe not abstract, but quite convoluted first time you see it. But let me assure you that this is, first of all, well defined. So this quantity is really going to be a positive real number so that I can take the 2d root. And it is going to be a norm. Homogeneity is easy to show. The triangle inequality is a little bit harder, but it is actually true. Those norms are going to be nested. So U1 is not quite a norm. It's a semi-norm. U1 is just the average value in the absolute, the absolute value of the average. Then U2 is going to be bigger than U1. U3 is going to be bigger than U2, at least perhaps up to some small constant, which we don't really care about. And all of those objects are going, and those norms are analogous to Gauss-Hostcraft semi-norms, which play a significant role in ergodic theory, and in particular in the study of characteristic factors for multiple recurrence. Here I'm not going to really say much more. If you know about this theory, then whatever I say is not going to be helpful. If you don't know about that then I'm not gonna be able to introduce it in less than another talk. Now, the main reason why I'm going to be now interested in
Sorry, what's the C in the expression there? There's a C to the power mod omega. Mod omega is, I guess, the number of ones.
Sorry, yes, I didn't. I missed it in the explanation. So C is the complex conjugate.
Complex conjugate of.
So I evaluate this value of f, and I conjugate it or I don't conjugate it.
I see. Okay.
And I conjugate depending on the sum of
Sure.
of binary digits.
Sure.
Well, the sum of ones in omega.
Okay.
Okay, so a significant reason why we are interested.
Explain the definition again of this Gauss norm?
Yeah, sure. So we take all, we consider all possible vectors n, which is n0 and 1 up to nd. Now we have we consider all the possible sums of a subset of those integers. So n naught maybe plus n1, maybe not, plus maybe plus n2, maybe not, and so on. And we're going to have 2d of those. So every second one of those values we are going to conjugate. If we add an odd number of ni's, we conjugate. If not, then not. We multiply all those things together. Then we take the average over all possible choices of n naught up to nd. And this is going to be the norm of f to power 2d. So the norm of f is going to be the 2 to d's root of the expression on the right-hand side. And I do realize that at this stage it might be a little bit unclear why we want to look at this thing, but that's the definition of it.
So it's like some kind of parallelograms in the integers, and you're evaluating the geometric mean along the vertices of the parallelogram, and then you're taking the expectation over all possible parallelograms. And is this one way to think of it?
Yes, that's very much one way of thinking about it. If instead of the initial segment I was working in Z mod and Z, I could give a slightly more intuitive definition in terms of repeated differentiation, but for now, that's the definition that we have. Okay, so the reason why this notion is useful, or at least one of the reasons, is that we have the so-called generalized von Neumann theorem. Oh, we have a new participant. So the generalized von Neumann theorem asserts that, well, if I want to compute some weighted sum of arithmetic progressions, say a d plus 1 term arithmetic progression, and each term I weight by fi, then this sum is going to be controlled by the UD norm. So this average is bounded by the smallest UD norms of the functions involved. Now, this has a nice consequence for us, that if we look at a plus or minus 1 valued sequence, and if we know that the UD norm is small, then the sequence looks random-like along d plus 1 term arithmetic progressions, in the sense that if we pick any pattern and we check how often it appears, it's going to be what you would expect if the sequence was random, plus an error dependent on the size of the UD norm. So in particular, if you have a plus or minus 1 valued sequence with such that all the UD norms tend to 0, then it's going to have maximal arithmetical subword complexity. Now, this perhaps shows that sequences with small Gauss norms are nice. Now, what sequences are there with small Gauss norms?
So the first statement is essentially saying that it's a normal sequence. If this is true, if you have this bound for all d, then you just get that the sequence is normal. Am I?
No, you don't get that it's normal. It could be the segments can still behave in some weird way. You get that it's kind of normal along arithmetical arithmetic progressions.
Progressions. Yes. So the gap is so you're looking at the number of pairs of n and m.
Yes.
Where I see.
Yes, so I'm basically picking a segment of length n, and I'm looking at a random arithmetical progression that's contained in this segment.
I see.
Okay. So perhaps this might convince you that looking at that sequences with that are with small Gauss norms have nice properties. Now, what sequences are there with that have small Gauss norms? Well, a trivial example is that we have, if you take a random sequence, it's going to be Gauss uniform. But anything you can show about the sequence, it's easier to show directly. So it's not a particularly useful example. It's just a trivial example to keep in mind. If you take a polynomial of degree d, and you consider the corresponding phase function, e to 2 pi I times the value of your polynomial, then as long as the leading coefficient is irrational, the ud norm is going to tend to 0, while ud plus 1 norm is going to be 1. So this is kind of a sequence that lies at the border between ud uniformity and ud plus 1 uniformity. A famous example of a sequence that's uniform is the Mobius sequence. This was proved by Green-Tau with the use of the inverse theorem due to Green-Tau and Ziegler. And this fact somehow encodes the fact that primes behave in a pseudo-random way, and that has the same philosophy as the Sarna conjecture. In a similar spirit, instead of the Mobius function, we can look at an arbitrary multiplicative function. And here, Franciszkianakis and Haas were able to show that, well, such sequences don't have to be uniform of all orders, but as soon as they are U2 uniform, so they don't have linear structure, they are UD uniform for all D. Now, when it comes to automatic sequences, quite a long time ago, I was able to show that.
Can you go back to the last slide? So you mentioned something was multiplicative in your initial slides. So I think you were referring to the Thue-Morse sequence.
Yes. So it was too multiplicative, which is a bit of a different notion than multiplicative. So multiplicative means that f of n times m is f of n times f of m.
I see.
Which is important in number theory. And too multiplicative means that that basically the value at n is the product of the values of some contributions depending on digits. In general, multiplicative sequences are a much harder subject to study than k-multiplicative sequences.
I see. Okay. So if you're multiplicative, then you're k-multiplicative for all k?
No. These are...
Then I haven't... I see. So they're not related at all. These notions
are
not
they're not related at all.
Okay, so then I
mean, they are kind of like a bit of a similar philosophy, but the two notions don't have any connection at all.
Can you explain the first example in the last slide?
The first example, the one about polynomials, yes? So,
yes.
So when it comes to the UD norm, there's a good reason why it's 1. It's basically, if you look at the formula for the UD norm, then you're going to have all of the terms are going to be exactly 1, which basically boils down to the fact that the discrete derivative of a polynomial, if you have a polynomial of degree d and you apply the discrete derivative d times, then it becomes 0. This translates to having the maximal possible Gauss norm. And when it comes to UD norm, well, basically, if you write down the expression, then it's you're left with some random coefficients, and it's going to tend to 0 because that's kind of the generic behavior. That's kind of what we would expect for a random sequence.
So where is the irrationality playing a role?
So, well, I suppose so. If the leading coefficient was rational, then the leading term of the polynomial would just introduce some periodic behavior.
Right. Yeah.
So from our perspective, it might as well not be there, and then f would behave kind of like a polynomial of degree 1 less.
Oh, got it. Yeah. I mean, I kind of got it. Yeah.
Okay. Okay. So let's come back to automatic sequences, which was supposed to be the main subject of the talk. Well, when it comes to automatic sequences, it turns out that the Gauss uniformity is quite easy to obtain. For instance, Thue-Morse sequence is uniform of all orders. And as a consequence, it's going to have the maximal possible arithmetical subword complexity 2 to n. And in fact, this is one of those theorems that get reproven every couple of years. Somebody comes with a new reason why that should be the case. This has been extended by Fried to some so-called symmetric morphisms, which I'm not going to define. We get the same result for the Rudin-Shapiro sequence. And in fact, you can get pretty much any sequence that corresponds somehow to pattern counting. Slightly in analogy with what Franzkinakis and Haas were able to do, together with Aihua Fan, we showed that if we have a k-multiplicative sequence, then U2 uniformity implies uniformity of all orders. Although, because multiplicativity is a much simpler notion than actual multiplicativity, this result is way, way easier than what they did. Okay, so if we have uniform sequences, that kind of makes us happy. We know how to work with those. So it would be nice to have a lot of automatic sequences that are Gauss uniform. And together with Jakub Byszewski and Clemens Müllner, we were able to obtain a pretty generic criterion. So specifically, we were able to show that in order for an automatic sequence to be uniform of all orders, it's enough that its U2 norm converges to 0. And in fact, for that, it's enough that the averages along any arithmetic progression converge to 0. So in terms of an intuition, this means that an automatic sequence can only have quote-unquote linear structure, and no quote-unquote quadratic structure is possible. And moreover, all those linear abstractions corresponds to abstractions that are in certain sense rational. Now, this is extremely vague, but let's see what we can do with that. So if we have, so let's say that we have a binary automatic sequence, and let's say that it has some density of ones along each arithmetic progression. And let's also say that this density is some number alpha, which doesn't depend on the arithmetic progression. For each arithmetic progression, it comes out the same. And it's somewhere it's strictly between 0 and 1. If we know that much, we can already say that our sequence has a maximal arithmetical subword complexity. There's nothing special about a two-letter alphabet. I just stated it that way so that the notation is a bit easier. But if we have a sequence over any number of symbols, and if each symbol has a frequency, and if this frequency is strictly between 0 and 1, and if it doesn't change upon passing to arithmetic progressions, we get maximal arithmetic subword complexity. And in fact, we can get some quantitative bounds.
So in your main result, which was a couple of slides back,
Yeah.
so there, you said that these are equivalent. And so the first proposition that you gave is a negation of that, which says that, oh, if it goes to something which is neither 0 or 1, then so it's giving one direction of the result, or no.
Right. Sorry, perhaps that's a little bit confusing. So we're not going to be applying the theorem from the previous slide to A, because it doesn't satisfy the property. We're going to apply it to A minus the constant sequence times A minus a constant sequence.
Okay.
So then the theorem says that A minus the constant sequence is Gauss uniform,
Sure.
and that we can use to prove things. Actually, we're going to see
Right.
if the time permits more or less how the argument goes. So perhaps then things are going to become a little bit clearer. So far we have seen that if our sequence, if the sequence under consideration is the sum of a constant sequence and a uniform sequence, then we can get some results, basically by applying the generalized von Neumann from a couple of slides ago. And it would be very nice for us if all automatic sequences had this form. Unfortunately, that's not the case. And there's going to be certain, there's basically three classes of sequences that give us problems. First of all, we have periodic sequences. Secondly, we have so-called forward synchronizing sequences. And here a standard example is going to be a plus or minus 1, depending on how many zeros we have at the end of the binary expansion of n. So this sequence is going to be very close to periodic, but not quite periodic. And we also have so-called backward synchronizing sequences. Here a standard example would be the minus 1, plus or minus 1, depending on the parity of the length of the binary expansion of n. And this is going to be constant on very long intervals. In fact, intervals, say, of the form n from n to n plus to n plus c times n, where c is some fixed constant. I suppose 1/10 could work. Those sequences are going to give us problems because it's not just that they're not uniform. They don't even have average values. So that's a bit of a problematic behavior for a sequence. And perhaps I should mention at this point that this sequence that has to do with length, it can be the nth term only depends on the leading digit of n, but not in base 2, but in base 4. Okay, so
Jacob, just a stupid question. I thought that automatic sequences are factors of substitutions, constant length substitutions. So don't we have that these are essentially minimal or uniquely ergodic or something like that?
We have that under assumptions like primitivity. Yeah,
right.
Yeah, but not all substitutions are primitive.
Sure. And you can't just break. Okay, so yeah, okay.
Yeah, so you can basically sort of build up like this is not a major problem. This is something that you can usually deal with, but you have to deal with. Okay. So I mentioned the notion of a backwards and forward synchronizing sequence, but perhaps the naming didn't really make much sense. So let me briefly explain what's synchronization. So an automaton is synchronizing if there exists a word W, a synchronizing word, such that no matter which state I start in, after I read the synchronizing word, I always end up in the same state. And now I call a sequence forward synchronizing if it's computed by a synchronizing automaton when I'm reading my input starting with the most significant digit, and I call it backward synchronizing if it's computed by a synchronizing automaton starting with the least significant digit. So here's perhaps the smallest simplest non-trivial synchronizing automaton on 2 states. Okay, so if we work with, when it comes to Fourier's synchronizing sequences, there's a very nice paper by Müllner, Schubin, and Spiegelhofer, who showed that who showed that not just arithmetical subword complexity is sub-exponential, but also that polynomial subword complexity is sub-exponential for those sequences. And I'm not going to talk much about this result because there's a very nice talk by Clemens on this subject that you can find online. In fact, I'm going to put up those slides at some point, and if you click the picture, it should send you there. So there we understand the subword complexity very well. So we're happy with uniform. We're happy with the standard examples of non-uniform. Now, there's going to be some sequences which are neither. And one way in which you can run into sequences like that is if you somehow combine the two in a and here's perhaps the simplest example of this happening in a slightly ham-fisted way. So imagine we have a Thue-Morse sequence along the even integers, and we have twice the Thue-Morse sequence along the odd integers. So this is going to be a sequence that looks something like this. And now if we look at the arithmetical subword complexity of that, we're going to basically have 3 classes of those. We have factors of Thue-Morse, we have factors of twice Thue-Morse, and we have factors of Thue-Morse shuffled with factors of 2 times Thue-Morse. So considering those 3 cases, we see that the arithmetical subword complexity of this sequence is, well, computing those 3 things independently, bounded by a constant times 2 to L, because in each of those cases, we're basically dealing with binary sequences. And the moral of this example is supposed to be that passing to some subsequences, we can reduce the alphabet size to 2. And this is going to be a bit of a general idea. But in order to put it into action, I'm going to have to introduce a little bit more terminology. I'm going to introduce a family APK of sets, which I'm going to think of them as a sort of a generalization of an arithmetic progression or a residue class. So these are going to be sets that are defined by specifying a residue of n modulo some q. But in addition to that, I'm going to specify the residue of the length of n in base k. I'm going to specify some prefix of n, and I'm going to specify some suffix of n. So specifying the suffix of n is basically specifying n modulo power of k. Specifying a prefix doesn't have a very nice interpretation like that. But in general, think of them as kind of arithmetic progressions plus some information about base k expansions. And with this in mind, I'm going to define the effective alphabet size, which is basically the smallest alphabet that you can get by the trickery like from the previous slide. So I'm going to say that a sequence A has effective alphabet size R if so this is so I'm going to define it for now as the largest integer such that I can pass to an APK set such that on every APK subset, I always see at least R symbols. And in fact, in this definition, it's always going to be, I can ensure that I always see exactly RA symbols. So intuitively, this is the smallest alphabet size that I can, intuitively, you can think that the sequence A is obtained by gluing together a bunch of sequences on alphabets of size RA. Now, let me give some examples. If I have a sequence that's either periodic or forward synchronizing or backward synchronizing, then always the effective alphabet size is going to be 1. Conversely, if we have the Thue-Morse sequence, the effective alphabet size is going to be 2. So whenever I pass through one of those sets, I always see 2 symbols. A couple of very basic properties. If I take the product of 2 sequences, then the effective alphabet size of the product is at most the product of effective alphabet sizes, could be less. And likewise, if I apply a coding, then it can only decrease the effective alphabet size. It follows more or less directly from definitions. So in particular, if I take any structure, and if in any way I construct a sequence out of those periodic synchronizing forwards or backwards, I'm going to stick with effective alphabet size 1. And now I can finally state our main result, which asserts that the arithmetical subword complexity of any automatic sequence is the effective alphabet size plus a small error term 2 power L. Now, let me make a couple of remarks about this result. So in one direction, we have exact inequality. We have at least the arithmetical subword complexity is at least R to L. And we can, in fact, find an explicit set of symbols with cardinality R such that we get all words over this smaller alphabet. The same estimate is going to hold for polynomial subword complexity. The effective alphabet size is something that you can actually compute if you really want to. I think it's fair to say that if the effective alphabet size is at least 2, then this theorem basically tells us how fast the arithmetical subword complexity increases. So it increases exponentially, and I can tell you what's the base of the exponent. Now, one thing that this unfortunately doesn't tell us is what happens when the effective alphabet size is 1. Well, it tells us something. It tells us that the subword complexity increases exponentially, but which sub-exponential function it is, that's an open problem, and we don't really have a very good understanding right now. And a quick corollary of this result, or actually of the proof of this result, is that if we have a maximal subword complexity, then all words appear quite often. So each word, if you pick a random arithmetic progression, each word has a positive probability that you're gonna find it. Okay, so in order to tell you a couple of words about the proof of that, at least in one direction, is going to require me to state our result with Byszewski and Müllner with a little bit more detail. So I'm going to need a notion of a structured automatic sequence. So I'm going to say that an automatic sequence is structured if it can be constructed from a periodic sequence, a forward synchronizing sequence, and a backward synchronizing sequence. So we already saw examples like that. They had effective alphabet size equal to 1. And we were able to show that each automatic sequence admits a decomposition into a structured part and a uniform part, where the structured part is structured in the sense mentioned above, and the uniform part is Gauss uniform of all orders. Now, I like to call it the arithmetic regularity lemma for automatic sequences, because it's somehow analogous to the Green and Thue arithmetic regularity lemma, which I'm not going to discuss right now because we are a bit short on time. Now, let me make a quick observation that if I have a structured automatic sequence, then I can always pass to an APK set where it is constant. It's basically by inspecting the relevant definitions that more or less falls out of them quite immediately. And from this, you can infer that whenever I have an arithmetic sequence that takes values 0 and 1, and if I'm in the situation, and suppose that I'm in the following situation, I have an APK set P, and whenever I pass to an APK subset Q, I can always find at least one value of n where an is positive. From this, it's going to follow that I can pass to an APK subset where a structured is constant and positive. So it's a slightly stronger statement than the previous observation. And from here, I can derive the following result. Let's say that I have an arithmetic sequence on R symbols with effective alphabet size R. Then I claim that I can find some smaller alphabet lambda and an APK set such that the structured part of the indicator of each symbol is constant and positive on P. And this is basically obtained by applying the previous lemma to repeatedly pass to smaller and smaller APK sets where each of those sequences becomes constant. And the definition of the effective alphabet size says that I'm not going to run out of symbols until I hit at least R of them. Okay, so with this background, I am finally able to actually prove one direction of the theorem, namely the lower bound. So the aim is going to be to show that the arithmetical subword complexity is at least R to power L. So let's take an alphabet lambda and an APK set P, like from the previous slide. And I'm going to, and I want to show that each word of length L, W appears in A along an arithmetic progression. So let's consider some large integer n. And let's say that we want to count how many L-term arithmetic progressions there are where W appears. Well, it's going, the result is going to be the sum over, let's be generous, n and m from 0 to n minus 1. And then we're going to have a product of terms where the first term says that the ith term of our arithmetic progression is supposed to land in P, our APK set. And the second term says that that at ith position we have Wi. Now, applying the generalized von Neumann theorem, we can infer that this count, that in this count, we're not going to make a big error if we replace each indicator AX with the structured part. Why is that? Well, if I write, if upstairs I write that this indicator function is the uniform part plus the structured part, and I open up all the brackets, I'm going to get 2 to L summand. This expression is going to be the first summand, and this is the one that I want to keep. And all the remaining ones are going to have at least one uniform function. And each of the uniform, and each of those sums can be bounded with the help of the generalized von Neumann. So at the end of the day, I chose my P so that each of those structured parts is constant. So each of those structured parts is some constant, say alpha W, that's positive. So my count is going to be just the product of all those frequencies times the number of L-term arithmetic progressions contained in P. And this is going to be basically some constant times n squared. So well, it's going to be a positive proportion of all n and m, and because of that, we we know that that our approximation is big, and that we didn't make that the error that we made along the way is small. So in particular, the main term is going to be bigger than the error term, and we conclude that at least that W appears at least once, and this is exactly what we wanted to prove. Now, I am out of time, so I'm not going to tell you too much about the other bound. I'm just going to end here, and thank you very much for your attention.
Thank the speaker for his talk, for his wonderful talk.
Thank you for giving me an opportunity to speak.
Questions? So, Jacob, I'm sort of curious about this effective alphabet size. Can you actually go back to the definition once more? It was sort of towards the end, and I didn't want to slow you down any further.
Yeah, sure.
Yeah. So one is given a sequence. It's the largest integer such that for any APK set, you have that the number of different letters that you see in a sub-arithmetic progression of an arithmetic progression is bigger than or equal to RA, and is the largest integer such.
Yeah. And so I guess the intuition here is somehow that I'm trying to pass to smaller and smaller APK sets to decrease my R as much as I can, and this somehow explains where I hit a stumbling block. If there's some P such that whenever I try to pass to a smaller APK, I always get at least R letters. So perhaps I can slightly clarify by saying one thing that I skipped for want of time. If I pick a sequence A with effective alphabet size R, then I can find sort of a decomposition where it's a little bit work to prove that it's not supposed to be obvious, but it is a true fact that I can find the composition of the integers into a bunch of APK sets. I'm gonna call them Pi and Qj, such that on each Pi I see at most R symbols, and on each Q and Qj's in total have density less than epsilon.
I see.
So I can sort of think that I have a bunch of I glue together a bunch of sequences on at most R symbols, and I have some small error terms. You could probably use this fact as a definition, but in practice it's easier to work with the previous one.
Yeah, okay. So I'm really thinking in terms of dynamics. So if there are versions of entropy, at least for symbolic systems. If you have a symbolic system, then you can do these things where you look at the symbolic system along an arithmetic progression, or you can look at a symbolic system along any kind of nice subsequence that you care about. And you're somehow, at least in this case, you're trying to it's not actually pinning down the entropy along subsequences. Okay, so you are trying to pin down the complexity along periodic subsequences, and you're doing it using this. Okay, it's quite interesting, but yeah, it would be nice to understand how to interpret these things dynamically. But yeah, maybe
Yeah,
that will require.
Yeah,
more
I
discussions.
very much I very much agree with that. If somebody can come up with a dynamic interpretation, I think that could be interesting. But that's not something that I'm aware of.
Okay, so other questions?
I don't really have a question, but I thank Jacob for the talk. I mean, like, this is all new to me, but it's very exciting.
Oh, thank you so much.
Okay, so maybe I'll switch off the recording. Where do I switch off the recording from? Sorry. Yeah, of course, I'll cut this all out from the